Hi everybody. So this video is going to go through step-by-step instructions for how you can make your own polariscope using the linear polarizing light filters from Snellius Minerals. So you should first check out the video on linear polarizers, which we'll link to here if you haven't yet. And if you need some linear polarizing light filters, you can purchase them here from Snellius Minerals. So in our video on linear polarizing light filters, we did talk a bunch about polariscopes, but I just wanted to do a more detailed step-by-step guide so that you can feel confident about building your own polariscope at home. So let's start out with a schematic diagram for a polariscope. So a very basic polariscope consists of a light source, a material to diffuse said light, a lower polarizer, an area where we can manipulate a sample, and then an upper polarizer. And the two different types of viewing that we're going to most use with our polariscope are going to be either viewing our sample with simply plain polarized light, in which case we've removed the upper polarizer, or viewing our sample with crossed polarizers. In this case, the upper polarizer is above our sample, but oriented so that it should block any light being transmitted through the lower polarizer, as the vibrational directions of our two polarizers are perpendicular to one another. So this was a schematic rendering of a polariscope. Let's actually build a polariscope step by step in detail. So the first thing we need is a light source. And you can use pretty much whatever you want as a light source. However, you should know that depending on the spectrum of light of your light source, you might actually get slightly different colors with your minerals. And we won't go any deeper into detail there because that is a rabbit hole of information for another day. But just note that if you change your light source, you may change the colors you actually end up seeing with your mineral. So for my light source, I chose a cell phone flashlight. And I haven't turned that on yet because it would just be an annoyingly bright light, at least until we get our next piece of our polariscope, which is a material to diffuse the light from our light source. So for my light diffuser, I'm going to go with a simple folded white sheet of paper. You could also use many other materials. Something like frosted glass would work as well. The idea here is to scatter the light from our light source while at the same time not messing too much with the spectrum of that light by imparting any particularly strong colors. So I've also put a bit of distance between my light source of my cell phone flashlight and my light diffuser of a sheet of paper, just using a couple wooden blocks. You can't see these, of course, because the paper's on top of them. But this distance between your light source and your light diffuser is going to be something you'll want to play around with, depending on your light source and your choice of light diffuser. So we're going to turn on our cell phone flashlight now that we have our diffuser in place, and we won't just be blinded by a bright light. And I'm also going to turn off the overhead light I have in this room. Basically, the less ambient light around, the better for seeing what's going on with our polariscope. So at this stage of our polariscope construction, the light that we're seeing is effectively normal light. It's light that has vibrational planes in all sorts of different directions. And so what we're going to do next is add our lower polarizer, and the light that passes through our lower polarizer will now be plane polarized with only one vibrational direction allowed to pass through. So we'll bring in one of the 2" by 2" linear polarizers from Snellius Minerals. These linear polarizers are cut so that the vibrational direction of light allowed to pass through the polarizer is aligned with one of the sets of the edges of our polarizer. So the light we're seeing now through our polarizer is plane polarized, but we can't tell yet if it's plane polarized in an east-west direction or in a north-south direction. We're going to have to do another test later to figure that out. So now to finish the construction of our polariscope, what we're going to also need is our upper polarizer. So let's bring in our second upper polarizer, and we're going to want to orient this upper polarizer so that we can view samples with crossed polarizers. Because we can see light through both polarizers at this moment, that means that the vibrational direction of light allowed to pass through our lower polarizer is actually the same as the vibrational direction of light being allowed to pass through our upper polarizer. So what we're going to need to do here is just rotate our upper polarizer by 90 degrees, and now we have crossed polarizers. So effectively, one of our polarizers is allowing light of an east-west vibrational direction to pass through it, and the other is allowing light of a north-south vibrational direction to pass through it. And so when you put the two together, well, no light's going through. So our two main viewing setups for our polariscope are going to be plane polarized light and cross polarizers. And our samples are going to go above our lower polarizer, but below the upper polarizer. So we have a polariscope now, but there is another additional piece of information that's going to be useful to us. And that's figuring out the different vibrational directions of light that are being allowed to pass through our polarizing light filters. So if we can figure out the vibrational direction of light passing through our lower polarizer, the vibrational direction of light through the upper polarizer will just be the opposite when we're at crossed polarizers. So there are a variety of ways in which to actually figure out the vibrational direction of light being allowed to pass through our polarizing light filter, but I'm going to pick the one that involves minerals, of course, because, well, if you're watching these videos, hopefully you like minerals. So we're going to use a tourmaline crystal to figure out whether our plane polarized light is vibrating in an east-west direction or a north-south direction. And this will make a whole bunch more sense to you if you remember back to our linear polarizer video and how we actually use tourmaline as a linear polarizer. Certain colors of tourmaline can actually work as linear polarizers because they effectively only allow light of a vibrational direction parallel to the long axis of the tourmaline crystal to pass through the tourmaline crystal. So let's bring in a tourmaline crystal while we have our polariscope set up for viewing a sample in plane polarized light and see what happens. What I want you to notice here is that the tourmaline behaves very differently depending upon its orientation. And I can now tell you that our lower polarizer is oriented so that the vibrational direction of plane polarized light coming through it is in a north-south direction. Just a few quick diagrams to help with explanation. We know that our tourmaline crystal only allows light that is vibrating parallel to the long axis of our tourmaline crystal to pass through. As such, if our plane polarized light was vibrating in an east-west direction, our tourmaline crystal would appear dark. Since our tourmaline crystal doesn't appear dark, that must mean that our plane polarized light is vibrating in a north-south direction. So you can also set up your polariscope so that your plane polarized light is vibrating in an east-west direction. You just have to then recognize that all your pleochroic end member colors will be shifted by 90 degrees from what I'm showing you here with my polariscope where the plane polarized light is oriented in a north-south direction. So we've gone over pretty much everything you need to do to set up your polariscope so far. But now let's go through an example of just testing it out and making sure it's working appropriately. You're going to want to use an anisotropic mineral and be able to identify pleochroism, as well as the extinction and transmission of light with crossed polarizers. So there's much more about what's going on here in the video Snellius Minerals isotropic versus anisotropic kit. And there's also a whole bunch more theoretical background in the educational optical mineralogy playlist. But for just testing out your polariscope, a mineral like tourmaline usually works pretty well. So in plane polarized light, tourmaline should exhibit pleochroism. That is, that it will change color as you rotate the mineral in plane polarized light. And in fact, tourmaline's rather extreme pleochroism is why it can be used as a linear polarizing light filter, with the caveat, of course, that not all colors of tourmaline operate as effectively in this manner. Let's bring in our upper polarizer now for our polariscope and take a look at our tourmaline crystal. And this is good so far. So we have the tourmaline crystal being extinct. As we rotate it, it starts to transmit light. It reaches a maximum brightness at a very particular angle, and then we can actually rotate it all the way to where it is extinct yet again. So this means the polariscope is operating appropriately, and we're ready to go to check out all sorts of different minerals. So hooray, we've built a polariscope! And since we've built a polariscope in detail, that should also help you understand the idea behind our LCD screen polariscope. In this case, the LCD screen is just effectively taking the place of the light source, the light diffuser, and the lower polarizer. And this is the style of polariscope that I'm going to be using in our other videos, as it provides a rather large work surface for plane polarized light that can be useful. So the polariscope that you see in my other educational videos is actually just this old iPad along with a linear polarizing light filter. And that's all you really need. So the sample would go in between our LCD screen and the upper polarizer, and you've got a cheapy polariscope there. Now, there's a whole bunch of caveats here. The first is going to be that don't use a shiny new LCD screen, because many of these minerals that we're going to look at are fairly hard and can easily scratch your new LCD screen. So what I'm using here is a 9-year-old iPad. It really doesn't have any other use at this point, so it's okay if it gets a little dinged up. Also, you can't have any of those tempered glass screen protectors on whatever LCD screen device you're using, because those have some stress in them and it ends up messing with our plane polarized light. Next caveat is actually the light source for our LCD screen. So our LCD screens are backlit, but they're backlit by a variety of different types of light sources, including LEDs and cold cathode fluorescent lamps. And so just depending on your screen, your colors might be different than the colors I'm showing here. And a final caveat here, OLED screens do not generate plane polarized light as LCD screens do. So some of those new fancy devices that actually are using OLED screens aren't going to work for this. So I hope after all this you feel really comfortable about polariscopes and trying to build your own polariscope if you are so inclined. So in this video we also used a tourmaline crystal to figure out the vibrational direction of our plane polarized light. And if you don't have one of those available to you, you should think about purchasing the isotropic versus anisotropic kit from Snellius Minerals, and there's a whole video specifically for how we can use our polariscope in order to determine whether or not a mineral is isotropic or anisotropic, and this is one of the first steps in identifying unknown minerals. Also, feel free to email if you have any questions, comments, or thoughts about these series of videos. Here are the references for this video. And I hope you're ready to use your shiny new polariscope to help identify minerals and understand the optical properties that they display. So thanks again for watching, and have a great day!